Good morning, students. This is our lecture for Friday, February 19th. This will be a recording that's in two parts. I'm putting these on YouTube, and there's a time limitation with that, so it'll be in two parts. So please be sure to watch both parts. Along that line, I typically put my slides up on Campus Web, but I'm at home and I have terrible internet service for some reason, and I'm really having difficulty working with Campus Web. So that's why this is going onto YouTube, and those slides won't be available until I'm back on campus. Along that line, as of right now, I plan on being in-person lecture on Monday. That could change, and if it does change, I'll let you know. But for now, plan on in-person lecture on Monday. I'd like to take a moment again to thank you for your flexibility here. This isn't ideal for anybody. I realize that it's difficult for you as well. And so I really appreciate your flexibility. I appreciate the well wishes and the prayers that I've received as well. So I'm at home. Like one of the advantages of that is I get to wear things like a Mr. Incredible t-shirt that I normally wouldn't wear on campus. Although when I get back to campus, I'm going to be in a cast for a long time, and I'm going to take advantage of that and wear my Hawaiian shirts and other things I normally wouldn't wear on campus. So I'm going to make the best of it. So a few points of where we're headed. The homework is posted, and hopefully you have seen that through the McGraw site. Several of you have already completed that homework that goes along with Chapter 6. With everything that happened, originally the due date was today, Friday the 19th. I went ahead and pushed that back till Friday the 26th. That said, I don't advise that you wait till the last moment. Just if you're able to get it done before then, go ahead and do that. You don't need to wait until the 26th to turn that in. Today we're going to continue with Chapter 6 in your textbook, which is about population ecology. And on Monday, we're going to wrap that up and then move on to some issues with human populations. Once I get back, if I'm on campus on Monday, I'll do my best to get those slides uploaded so you'll have that to go along with it. If you have any difficulties, please let me know as well. So I've told you a little bit of what happened with me. I had a slip and fell and broke the upper bone in my arm, the humerus bone, which is like the second largest bone in the body, and had some complications from that and had to have a surgery on Sunday to try to put it back together. And right now I'm doing okay. I know that it's going to be a bit of a long road here. We normally start with a joke, and I try to solicit a joke from you, and I can't do that. So I was going to tell you a joke about a broken arm, but I don't think it's very humorous. Hopefully you got that joke. Before I go into a review of what we talked about before, I want to take just a moment to talk about weather contingencies and things. So this last week was a rough week, especially for me, but for our commuters and people coming on and off of campus. Hopefully we're out of that weather. But for those of you that are commuters or those of you that are on campus, please know that I'm very flexible when it comes to that. I don't want you to put yourself at any sort of risk. If it's dangerous outside, if you have a hard time getting out of your home or out of your dorm or whatever, let me know. You don't have to let me know before class. Let me know eventually, and we'll work it out. Just know that I'll work with you on that. And please, if we end up with bad weather moving forward, don't put yourself at any sort of risk, please. All right, so we talked about population ecology and went through some terms. I gave you this example with this Sasquatch. I'm going to do just a very quick review, and then we're going to move forward. So some of the terminology here, when we talk about populations, we use the large N to denote a population. So in this example, 10 Sasquatches, the population is N, so N equals 10. The rate of change is the rate of change over a specific period of time. So if we have 10 Sasquatches in 2021 and we have 11 Sasquatches in 2022, the rate of change is 10% per year. We often denote that with an R, and R is like the multiplier that comes up with that rate of change. So in that example, if we were going from 10 Sasquatches to 11 Sasquatches, that's a rate of change of 10% per year. R would be 1.1. So if you took 10, multiplied it by 1.1, you end up with 11. If you multiplied it by 1, there's no change. So if you have an R that's 1, it's a stable population. If it's less than 1, it's decreasing. If it's more than 1, it's increasing. We denote time with T. Often with the things that I deal with most with animals, we're talking about a year, but that could be case specific. So our example going the other way, if we had 100 Sasquatches, our population is 100, or N equals 100. Next year, we have 90 Sasquatches, so we had a 10% change. So the rate of change is a negative 10% over a year. So R in that case is 0.9. So if you took 100, multiplied it by 0.9, you end up with 90. We talked about this term of exponential growth. Sometimes it's called geometric growth. There's a little bit of a difference between the two, but for our purposes, we'll use them the same. This is a constant rate of growth with no time limit. So this is good if you have a retirement account. You want an exponential growth of 10% a year, year after year after year after year. And natural populations, this rarely happens, or it doesn't happen. There's always something that limits it. But exponential growth is assuming a constant rate of change over time. One reason that we don't see exponential growth in natural populations is because of this concept of carrying capacity. Carrying capacity is the population that can be supported by a given area without depleting all the available resources. We denote this with the term or letter K. I don't know why we use K for carrying capacity, but that's standard notation for that. And when you think about populations like the moose example we had last time, typically populations start below a carrying capacity, and when they're below a carrying capacity, there's lots of resources available. So that population grows very quickly. It often overshoots or goes above carrying capacity for a short period of time. But once it's above carrying capacity, resources become limited, and that causes negative effects on the population. So there's a dieback that happens. A population will die back, it'll fall below carrying capacity. Once it falls below carrying capacity, resources are abundant again, and it overshoots carrying capacity. And so you end up with these oscillations, these boom and bust oscillations bouncing around carrying capacity. Rarely does an animal population just hit a carrying capacity and stay there, but rather it goes above and below, above and below. So limiting resources are what slows exponential growth and what limits exponential growth. Often a population's rate of change will slow as it approaches carrying capacity. This is pretty realistic. So we end up with a growth curve that looks kind of like an S. If you drew out an S in front of you, it moves kind of quickly, and then as it approaches some line, it kind of levels off again. Also called a sigmoid curve. We call these logistic growth, that as a population approaches carrying capacity, the rate of growth slows down. Here's a mathematical formula for that. I don't necessarily need you to understand or memorize these mathematical formulas, but what I want to point out here is just that last part. So we have Rn, so that's a rate of growth for a population, and then it's multiplied by this weird looking thing, and it's 1 minus n over k. So if you can imagine, if you had a carrying capacity of 100 and you had a population size of 100, then you have 1 minus 100 over 100, which is 1. So then you have 1 minus 1, which is 0. So if you took 0 and multiply that by the growth rate, you have essentially no growth rate. So this is a way of mathematically depicting that. Again, don't get too hung up on the formulas. Just know that there are mathematical ways to describe this that have been worked out over time that seem to do a fairly good job of describing these things. So this is an illustration of that logistic growth or a sigmoid growth curve. That is what that mathematical formula would depict as well. So in this example, these are wolves. It's not a very good illustration of a wolf because they don't have the tail right on it, but that's a whole other story. You could see the population, this blue line, that S curve is the growth rate in the population over time. And while it's significantly below that yellow line, or the carrying capacity, there's a pretty fast rate of growth. But as it approaches the carrying capacity, it levels off to the point that there's no real rate of growth because it's approaching carrying capacity. Logistic growth is a form of density-dependent population growth. So what that means, density dependence, is that the growth rate depends on how dense the population is at the time. There are some factors that impact the population differently depending on how high the population is. So some common density-dependent factors would be things like disease. When populations are high, there's higher encounter rates between individuals and disease moves quickly. So the impact of disease might be higher when the population's high just because the transmission rates are higher versus when it's low. Physiological stress, like limiting food resources. When you have lots and lots of animals, there's less food resources available, and that causes physiological stress on the body. Versus if you have a lower population, there might be more resources for them to share. Predation can also be density dependent. If you have predators that avoid an area because there's not very many prey in there, that would be a form of density dependence. And conversely, if there was a lot of prey animals that supported a lot of predators, that could be a form of density dependence as well. So there are several different areas where we see density dependent factors that impact the rate of population growth and rate of population change.